Hi everybody. This is another video in my series on computer systems. In this video we'll be talking about Module 2. This is part 2 of that module. In part 1 we talked about some of the basics of machine code that you need to know to understand what's going on with it in general. And in this video we'll get into control. So we'll talk about things like conditionals and loops when we're dealing with machine code. Now, there are some parts of the processor state that are of particular interest when we are talking about controlling the execution of a program. Now, we get temporary data in something like RAX. We've talked about how RDI and RSI get parameters, etc. But what we want to focus on are, first of all, RSP. Now remember, we keep saying, stay away from that. Let's not just dump data in there or something. And the reason for that is that this is the stack pointer. This is the location of the runtime stack. And RSP always points at the current top of the stack. And that's why we don't want to mess with it. Because, of course, the stack is very, very important when we're running a program. And we'll get into that in more depth in future videos. But that is one thing that we really want to pay attention to. We're going to have in RIP that instruction pointer. Intuitively enough, that's the location of the current code control point. That's just pointing to the next instruction to be executed. And we have the status of recent tests. These are referred to as control codes, this CF, ZF, SF, and OF. So let's take a look at what those mean. Now, our condition codes can be set either implicitly or explicitly. So we can assume that they're going to get set by various operations, or we can actually go ahead and call commands that set them directly. Now, these are single bit registers because they're flags, right? So we only need one bit. It's going to, 1 for on, 0 for off. And we've got CF, our carry flag, ZF, our zero flag, SF is the signed flag, and that's for signed operations, and OF is the overflow flag. Now, that's also for signed. That's for overflow of 2's complement operations, whereas the carry flag, CF, indicates overflow for unsigned operations. Now, these can be implicitly set, and we can think of that as a side effect by arithmetic operations. So if we just do an add, right, we add a source to a destination and dump the result into that destination, then the carry flag would be set if there's overflow from an unsigned operation. So if there's carry out from the most significant bit, then we'd have the carry flag set. The zero flag would be set if the result was equal to 0. So if I add A and B and the result that I get is 0, then we'll set the 0 flag. The signed flag would be set if the result was less than 0. And the overflow flag would be set if there's 2's complement overflow. Now, these are not set by the load effective address instruction that we talked about in the last video. So we want to kind of keep that in mind. When we do an add, these flags will get set without us doing anything, right? That's why we call it an implicit setting. However, keep in mind there are other instructions like load effective address that do not end up implicitly setting these flags. So we want to be kind of careful that we keep in mind which instructions will set flags and which won't, because we need to know that. We have to understand that in order to use these flags to control the flow of our programs. Now, there are also some commands that we can use to explicitly set our flags. So when we use these commands, we're not actually going to mess with any of the other registers. The only thing we're going to do are set these condition codes. So one option is the compare instruction, CMP, and it's kind of like computing a subtraction, but without actually setting a destination. So we can just give it 2 source registers. In this case, we have it set up as source 2, source 1, because remember, with machine code, in a lot of these, we're doing things sort of the opposite of what we would normally think of in C. So if I want to compare A and B, then this command is like computing a minus b, but I'm not going to set a destination. I'm not going to preserve the result anywhere. I'm just going to do the computation and throw out the result, because all I'm trying to do is set my flags. So if there's carry out from the most significant bit, we'll set the CF flag. If A is equal to B, we'll set the 0 flag, right? Because at that point, A minus B would be 0. If A minus B is less than 0, we'll set the sign flag. And if there's overflow, so, if A is greater than 0 and B is less than 0, and A minus B ends up being less than 0, that's weird, right? That doesn't make a whole lot of sense. That when we think about it from just the perspective of abstract algebra, well, that should end up being a positive value, right? So if it's negative, we know that there's been a signed overflow. On the other hand, if A is less than 0 and B is greater than 0, well, then A minus B should definitely give us a negative number. If that ends up being positive, well, then we know something weird must have happened, and that's the kind of thing that happens when we have overflow with 2's complement. Now, we can use the test command to set our condition codes in a slightly different way. In this case, test is like computing A and B without setting a destination. So we can end up setting kind of a subset of flags, right? Because if we're doing an AND, when we just do our bitwise AND, we're not going to overflow. We're never going to overflow by doing a bitwise logical operation. So with this one, we can set the 0 flag or the sign flag, right? Because A and B, if that equals 0, right? If I do this bitwise and the result is just a bunch of zeros, then that will set the 0 flag. If we're looking at this as a signed number, right? If this is 2's complement and we have a 1 in the most significant bit, well, then that means we're dealing with a signed value. So we can set the SF flag, and then we just won't end up with any kind of carryover or overflow, obviously, right? So we won't have the carry flag and the overflow flag being set from a test instruction. So this is a useful thing to use with a mask, all right? If I want to have a mask that I want to apply, I can just go ahead and directly specify one of the values and then compare it to something else to set my condition codes that way. Now, once we've gotten our condition codes set, sometimes we're going to need to read them, right? For example, what if I have two values, x and y, and I just need to find out, is x greater than y? This is the kind of thing we use for controlling our program flow all the time, right? Think about pretty much every condition you put in for an if-then statement. They tend to be some sort of comparison. So we can use the set instruction to access our condition codes, and the way that the set instruction does that is by setting the low order byte of whatever destination register I give it to either 0 or 1 based on the combinations of condition codes. Now remember, with our registers, we can access different parts of the register, right? If I give a register, if I give RSI, I don't have to just use the entire quad word, right? I can reference, I can kind of like dive into that. I can look at the lower order 32 bits, the lower order 16 bits, or I can look at the lowest order byte. And that's what set X deals with. It doesn't alter the remaining 7 bytes in the register. Now, the way set works is by looking at the condition code to figure out, whether it's going to set that byte to a 0 or set it to a 1. And that ends up being equivalent to a whole bunch of different comparisons that we might do. So if I'm comparing X and Y, right, and I use compare and I do, so I'm going to do X minus Y, well, the 0 flag is going to be set if they're equal to each other. So I know that they're equal if a compare yields the 0 flag being set. I know they're not equal if it doesn't. So if we have not ZF, if ZF is 0, then we know that those two values are not equal. If the sign flag is set, then that means that that subtraction has yielded a negative value. this is a good time to actually pause the video and take a look through this table and make sure you understand what all the different options are for set, because these are basically the same things that we're going to do for jumps later on, which when we get directly into control. But this is the kind of thing that when you do some kind of comparison, like in an if-then statement, this is the kind of thing that's going to happen to get you that result. So here's an example that actually goes through that thing that I just mentioned. Let's say we want to compare X and Y. So we're just going to return X greater than Y. Now, remember, when we do a comparison like this in C, well, that's just going to yield a 1 if X is greater than Y and a 0 if it's not, right? A true or a false, and that's what we'll return. So this little function just does exactly that. It just says, look, is X greater than Y? So when we dive into the machine code, our DI will get argument X, our SI will get argument Y, and then our AX, as usual, is our return value. So we can use the set instruction to set that single byte based on the codes, and then we're typically going to use a move command to finish the job. And it's important to note that when we use a 32-bit instruction, even on a 64-bit architecture, we also set the upper 32 bits to 0. So a lot of times when you dive into machine code, you'll see registers referenced with the E instead of the R, right? We're talking about RDI, RSI, though this R indicates a 64-bit, a quad word register. The EDI, ESI, EAX, those are our 32-bit portions of those registers, the lower order 32-bit portions. But if I do a move and I move something into EAX, I'm going to move from my source into that lower order 32 bits of the AX register. But because I've done a 32-bit instruction, it's actually going to, by default, just zero out the upper 32 bits. So this is a way that, again, compilers are smart. This is a way to save some clock cycles. I'll move a certain amount of data and then just zero out the rest because that's cheaper rather than moving to the entire 64-bit. So doing this 32-bit instruction and then by default zeroing out the upper order bits saves me some clock cycles over doing a 64-bit move instruction. So this is yet another thing where the assembly doesn't necessarily map one-to-one to kind of what you would expect. There's some stuff happening by default that makes things go a little quicker for us. So moving into the assembly code itself, we can use that compare instruction that we talked about to compare RSI and RDI. Right, so we're taking X, comparing it to Y. We're effectively doing an X minus Y. And then if greater than, so that's that set G, we'll set if greater than AL. So that sets when X is greater than Y. And you can go back to the set slide to take a look at exactly what the Boolean algebra is for that. But the point is we've used this to dive into our flags, find out whether X is greater than Y. Then we'll use that move instruction, this move ZBL. Ooh, boy, what's that mean? Means we're going to be moving but zeroing out the upper order bytes. Okay, and we're addressing L, so we're addressing the low order byte of AL. So that just means we're going to take just that lowest order byte of AL, move it into EAX, and because we've used MOVZ, we'll zero out the other 3 bytes. So we'll move whatever's in AL, that lowest order byte, and zero out the rest of the 24 bits to get us to the 32-bit value that we move into EAX, which by default zeroes out the rest of RAX, and then we'll go ahead and return. And what that's done is just ended up giving us our return code, our 0 or 1, in EAX, which again, we've zeroed out the upper bits, so RAX is just going to be that Boolean value. It's going to indicate that true or false for us. And that brings us to jumping. Our jump instructions jump to different parts of code depending on the condition code. So we're going to look at the condition codes and evaluate them in the same way that we did with the set instruction. right? All of this Boolean algebra holds, but instead of just setting the lower order byte of a particular register like we do with set, with jump, we're actually going to jump to a different part of the code depending on what the condition codes tell us. And again, this, whether if it's negative, it's greater, if it's less than or equal, all right? These are the kinds of things that we see with conditional and loop conditions all the time. So let's take a look at a quick example, a little snippet of C code that just takes the absolute difference. All right, so when we're dealing with an absolute difference, the order in which we process the operands matters, right? We want to get a positive representation of the difference regardless of the signs of things or how big they are in relation to each other. So what we can do with that is do a comparison, right? We can say, hey, if x is greater than y, then we'll subtract y from x. We'll do x minus y. Otherwise, if x and y are equal, or if y is greater than x, we'll do y minus x. So that's simple enough, right? We just do a little comparison, find out, is x greater than y? If it is, okay, great. We do x minus y. Otherwise, we do y minus x. Now, let's take a look at how we use a jump instruction to do that in assembly. And jumps are very much like Goto in C. Way back in the day, we always kind of hear, oh, never use Gotos, we hate Gotos. But this is kind of how assembly does it. So we've got labels. We've got labels for our function itself, so that absdiff colon there. That's the label in the assembly that tells us, hey, here is where the code that's called absdiff lives. And we'll also create another label, this .l4, and that's just kind of a standard notation. That's just another label that we're going to use to tell us where to jump to if we jump. We can use a compare instruction like we talked about a few slides ago, compare x and y, and then jump if less than or equal, right? Because if it's greater than, we just continue on to this move and subtract commands and then return. However, if x is less than or equal to y, we'll just jump straight down to this .l4 and do that other set, the set that's of instructions that's in red. And that's how we've given ourselves this if-else statement reflected in assembly. So let's move on to loops. Because all of this, jumping and go-to stuff is fine, but how does that help us with some of the more common things that we see when we're dealing with high-level programming languages like C? And so we'll talk do-while loops, for loops, while loops, right? Well, the good news is we can convert basically any of those things into a version that uses Goto instead of using the loop structure that we're used to. And that means we could, to understand this, we can actually take, say, a do-while loop, convert it to a Goto version, and then convert that into, right, the Goto stuff maps to our jump commands in assembly very nicely. So let's take a look at an example. This is something that just counts the number of ones in an argument. So we'll use a conditional branch to either continue looping or to exit the loop. So first things first, let's take a look at this C code on the left. Now remember that with a do while, we always do the stuff within the loop one time, then we do our comparison, right? We do our little, hey, is x something other than 0 in this case, right? And then if that's the case, we go back to the do. We just keep on doing that. We keep looping through until the loop condition is no longer satisfied. So in this case, we're just going to add x bitwise ANDed with just 1 to our result, right? So that's just going to look at the lowest order bit of our input x and add 1 to the result if that lowest order bit happens to be a 1. Then we'll take x and right shift it by 1. Okay, so we'll just sort of move it over 1 so that that next bit is now in the lower order bit. We'll find out, hey, is X just a bunch of zeros? If not, we'll go back to the do, and we'll just keep on doing that over and over again until we've gone through and we've got nothing left. We've got no positive weight left in X. Now, the Goto version is very straightforward. It maps almost one-to-one. We just add this little label here called loop. We do the same operations, and then instead of that while X, we just do an if X. If X evaluates to true, again, if X is anything other than 0, we just go to loop. This does exactly the same thing. And now we can dive into the assembly based on that Goto version. So we've just used the Goto as a little transitional step to go from a maybe more complicated loop structure from a high-level language. Again, we're still in that high-level language, actually, with the Goto, but we've simplified things in a way that, as we can see here, maps a little more directly to assembly. So when we go through the assembly, this is just about a one-to-one thing, right? We move 0 into EAX. That's just zeroing out the result. And remember, when we move it to EAX, that's going to zero out the upper order 32 bits of RAX by default. Then we've got our label. That's our loop. In this case, in the assembly, it's .L2, but that's okay. That's still the label that we use as where we're going to jump to when we loop. We'll move RDI into RDX. So we're just going to move our argument into a different register to preserve it. We're going to do that and, right? That's straight out of the code, right? We and X and 1. And then we're going to move that into EDX. We're going to add RDX and RAX. That's just adding 1 to the result. We're just incrementing the result. And then we're going to shift our RDI. We're going to shift our input and then jump if not equal, right? Remember, not equal means that the 0 flag's not set. And so that's basically exactly what that if X does. If it's 0, we fall out and just keep on going and return. If it's anything other than 0, then the not equal, the 0 flag won't be set. That not equal will be true. And we jump up to the loop label L2. So in general terms, when we're looking at a do while, we can translate that to a Goto version by basically following this very simple little method here. In C code, we've got do, and then we've got the body, which is just our statements, right? That's just a bunch of like, what are we doing within this loop? And then we have the keyword while, and then we have the test, right? So while the test is true, we keep looping back to the do and going through and executing the body. In the Goto version, we're going to add a label called loop, then we have the body, and then we just do an if test. And then if that test is true, we go to the loop label. So it's very, very simple, right? This is almost one-to-one. So it's an easy translation to do. Now, with a while loop, it's very similar to a do while, except whereas with the do while, we actually do the body. We execute the body at least once every time. Then we check the condition to see if we're going to loop again. With a while loop, we actually check the condition first. So with a while loop, we might never execute the body at all. So we've got to deal with that in our Goto versions in a slightly different way. And there are a couple different options for doing that. So let's take a look at both. First is our jump to middle translation, where basically we're just going to have a separate label for our test. So I've got the same kind of stuff that we saw in the do while loop. We've got our label for loop, and that gives us the body of the loop. Then we're actually going to have another label for test, where we'll actually do the if test go to loop. So that's the same, but we give that its very own label. And up at the top here, we actually do a go to test. So we're actually going to jump to the test, execute that, and then go back and execute the loops if we need to. So it operates in a very similar way. And that's just how we're going to actually do the test first before we do the loop even once. So since I do love examples, let's take a look at an example of that pop count function, but in the form of a while loop instead of a do while. As you can see, it operates the same way, right? That result plus equals x and 1, the right shifting x by 1, these all are exactly the same code as we had in the do while. It's the same body. The only difference is we do that test up in the declaration of the while loop, so we never run through this even once. So our result would be the same. I mean, even in the do while, if we ran through that once, we ran through the body one time, if x was 0, well, then that and would yield to 0. Our result would be the same. But by using the while, instead of running through the body once and doing the test, we just do the test and then skip right out of it. So this saves us some clock cycles. Now, over here on the right, the jump to middle Goto version, all we're going to do is put a little gatekeeper up at the top. We're going to say, you know what, go to test before we get to the loop. We'll jump down to the test, do our condition. If that evaluates to true, we'll go back up and execute the loop, and then we're right in exactly the same code as we dealt with the do while translation. And of course, if x is 0, then we fall out and simply return our result. Another option is to actually do a label for done instead of a label for test. And in that done label, we're just going to return the result. So up at the top, instead of going to the test and then potentially going up to the loop, we'll just find out, do we need to run the test at all? If not, we'll just go to done and skip the loop completely. Otherwise, we'll fall through, we'll execute the body of the loop, then run the test, go back to loop if we need to, etc. Then once that test fails, we fall back down and return our result that way. So it's pretty much the same thing. It actually accomplishes the same outcome, but we just do it in a slightly different way, where instead of jumping to the test, doing the test, and then jumping to the loop or not, we'll kind of do the test and then either exit to done or fall through and do the loop. So again, same idea, just slightly different ways of attacking it. Moving on to another very, very common form of loop, the for loop. In this case, we remember with the for loop, we don't just have our test in those parentheses around the loop declaration. We actually initialize something, and then we do our test, and then we do an update in our for loop, and then everything else happens in the body. So if we take a look at our for loop version of pop count, where we have the loop, we've got for I equals 0, we have I less than W size, which we've defined up at the top, and then I++, we're incrementing I. So we've got a loop counter, and as long as it's less than that size that we've defined up at the top, we'll execute the body, then we increment the loop counter, do our comparison again, and as long as I is still less than W size, we execute the body, increment the counter, and so on and so forth until that test fails, and then we drop out, and in this case, we'll just return the result. Now, the nice thing is, again, we can always convert a for loop into a while loop by just sort of breaking out the initialize, test, and update parts and the body and putting it into a while loop form. So we can just take that initialization step and do it right before we declare the while loop. Then in the while loop, we just have the test like normal. We do the body, and then we just put that update down after the rest of the statements in the body. So we can just break out the component parts of the for loop declaration and put them in the right spots in code, and out pops a while loop. And we've already seen we can easily go from a while loop to a Goto version, which maps nicely to assembly. So the point of this kind of section here was to point out that these loops and the high level stuff, they're different forms and they work well for different kinds of things when we're in a high level programming language, but we can always convert them out. We can always tear them apart into their component parts to get to the point where we can sort of easily see how the whole control flow would map into assembly. Now, a really handy thing to take a look at as an example to show us, again, some things that we can do to make things make a ton of sense in assembly when we're coming from these high-level structures is let's look at an example switch statement. We'll just call it switch_EG for switch example. We're going to have 3 longs that we're going to pass into it, and we'll return a long called W. So the first thing we do is kind of set things up. We're just going to initialize W to 1. And then we have our switch. We're going to switch on X. In case 1, we'll set W equal to Y times Z, then we'll break, so we'll just get out of the switch. In case 2, we'll set W to Y divided by Z, but then we're going to fall through. Notice we have no break there, so we just fall through and keep on executing right through case 3. So we'll take W and assign the value of Y divided by X to it. Then we'll increment W by Z, then we'll break. So we're going to divide Y by Z, set that, set W equal to that, then add Z to W, then we'll break out of the switch. And notice that case 5 and 6 are multiple labels for the same case. So if I have a 5, I'll do this decrement W by Z and then break. If I have a 6, I'll do the same exact thing. Our default is W equals 2. And notice that we have a missing case. We don't have a case for 4. So that if it's 4, it'll just go to the default. And if it's anything greater than 6, we'll also just do the default, right? If we don't have a case for what we're switching on, we just do the default and then return. Now, before we dive into the assembly, let's take a look at an idea of something called a jump table. So we have our switch form over here on the left. Now, this is a look at a general form of a switch, right? We switch on some variable X, and we'll have n cases, right? So for the case of value 0, say, we have block 0. For the case of the second value, val 1, we have block 1, and et cetera, and so on, all the way to the case on the specific value of X, n minus 1, our last specific case that we want to deal with, that's going to go to block n minus 1. Now, we'll have a jump table out there somewhere, and that's got the addresses or labels for all of those targets, target 0 through target n minus 1. And what we'll do is, for those cases, we'll translate those into a Goto, where we'll say Goto and then go over to the jump table to whatever index, to the index that corresponds to the value of the variable that the case matches, and we'll go to the address in memory that's reflected in the jump table, right? So the jump table holds our addresses. We're just going to go to the appropriate index within the jump table, find our address there, and then jump out to those targets and execute the code, because that's where those code blocks live. So let's start translating this thing. Let's start taking that switch that we saw a couple slides ago and actually turn it into assembly. Now, the first thing we do is set things up. We'll have our registers with our standard uses, right? Our arguments go into RDI, RSI, RDX. Our return value will be coming out of RAX. There's no surprises there. And let's just take a look at a few lines of assembly that will handle some stuff for us. So first, let's move RDX. Let's move argument Z into RCX. That'll be useful later. So we want to remember that happened. We'll see why that happened in a little bit when we get into the actual cases. We'll compare 6 with RDI. Now, why is that? Why are we using 6? Well, if we go back to our switch from a couple slides ago, we'll see that the highest number that we have a specific case for is 6. Right? That's the 6 kind of defines the range of our enumerated cases. So we'll do a comparison, and that's going to set those flags that we talked about right at the beginning of the video. Now we get into a jump. Now JA is jump if above. So basically, if we compare 6 to RDI, right? If RDI, if our argument X is above 6, if it's greater than 6, we're going to jump to label L8. And again, we'll see what that is in a little bit. Otherwise, we're going to jump to, what's this star L4? Well, it's called an indirect jump, and it's just like a pointer. Okay, so we're going to go to label L4, and we're going to go to a certain displacement. Remember, we have this form that we saw in our last video. Now, this means we don't have a base register. We do have an index register, and we're going to multiply it by 8 because we're dealing with 8-byte words. All right, so that's why our scale factor is 8. So we're going to go to label L4. We're going to start there and go to an offset. We're basically going to go to as many words as argument X specifies down from L4, and that's our index, right? That maps, it's like an array, right? Our index, if X is 1, then we'll go 1 word away. If X is 5, we'll go 5 words away from L4. And then we're going to treat the value that's stored there as an address. And that's what that little star does for us for that indirect jump. So by doing that, we just see that our jump table maps to the various cases, right? So we take the case, we use that as our index to jump to the appropriate label within the jump table, which starts at the label L4. So for case 1, we'll jump to L3, right? We go to L4, we go offset by 1. If we offset by 0, we'd be at L8. If we offset by 1, we see, there's an entry for L3. When we do that indirect jump, we'll actually just go to L3. We would end up looking at what's at L3, treating it as an address to go get the code block for case 1. Case 2 maps to L5, case 3 maps to L9, case 5 maps to L7, case 6 also maps to L7, and that's because those 2 cases have the same code block, right? So we just map those out to a single code block lives out there, and either one of those map to that. What about case 0? What about case 4? Neither of those is above 6, right? Those are cases that are below 6 that could be possible values, but they, don't have a specific enumerated case. Well, those are going to go to the default block. So we can figure out that, L8 must be the default block, and that makes a ton of sense, doesn't it? Because back in the setup, when we looked at the last couple slides, we saw that if the input, if X was greater than 6, we went ahead and jumped to L8. Okay, so L8 is just the default case, so that makes a ton of sense. So if we're outside of our range of valid cases, we'll just go to the default. If we have a case that's within the range but is not specifically enumerated, we also go to the default. So now that we figured out how to get to our code blocks, let's take a look at what those code blocks might look like. Case 1, perfect example. We saw from the jump table that that's going to map to label L3. So over on the right here, we have the assembly. What we're going to do is just calculate y times z, drop that into w, and then break. And all we're doing after we break is returning w, right? So what we want to accomplish here in this code block is to multiply y by z and return the result of that value. And remember, the return value is always going to live in RAX. So this is pretty simple, right? We're going to move RSI to RAX, and RSI has y. So we'll just take y, dump it into RAX. Then we'll multiply y times z, store the result of that in RAX. Oh, hey, look at that. We've got the result of y times z sitting in RAX, which is where the return value lives. So then we just return. So nice and simple. A pretty much, again, one-to-one kind of thing. The only thing that's a little weird is using RAX as the target on those commands, and we're only doing that because we're directly calculating the return value, and the return value is going to need to end up in RAX anyway. So we just kind of use that as our almost an accumulator kind of thing, where we just make sure that the end of all our operations lands in RAX, and then we can just call a ret, and we've returned our value properly. Now, to handle the fall through for case 2 and case 3, in this case, we're actually going to have a few different labels. We're going to have a case 2, right, that lives out there somewhere. We're going to have a case 3 that lives out there somewhere, and we're going to have something we're going to call merge. to deal with falling through from those cases. So if we were to call case 2, we'll just go ahead and do y divided by z, and then we'll go to merge, which is going to increment w by the amount of z, right? And that's the code that we see in case 3. Now, if we just directly call case 3, that's where we're actually going to initialize w, right? Because note that when we did the setup, there was a note on the slide that we didn't actually initialize w during the setup, and that's because there's only one spot where we would need to initialize w. Is it only if we call case 3 do we actually have to initialize w, and hey, that initialization, that's an assignment, that takes some clock cycles, so let's optimize it right out of there. Let's only do that if we have to. So that's why in this particular case, we ended up breaking it up this way, so that we can save some clock cycles on that initialization and only do that assignment if we actually have to. Now we have another bit of assembly-specific kind of weirdness to deal with. CQTO. What's that? Well, idiv, which is our next thing, where we actually do the division, y divided by z, actually does a 128-bit divided by 64-bit division. The way it does that is it sign extends RAX to RDX. So our dividend is going to be RDX and RAX kind of put together into one big 128-bit thing. So CQTO just sign extends RAX into RDX. And the reason we can do that without tromping on the value of z is because we moved that during our setup into RCX, right? When this code got generated, when the assembly gets generated, it anticipated that. It saw that, oh, this is going to be a thing that happens. It moved z into RCX. So now I've extended RAX to be RDX and RAX appended. I then divide that by RCX, which is our value of z. Now I've got my result of y divided by z, so I can just jump to L6, which is our merge. Now remember that merge is actually what has the code that was in case 3, so we're going to add RCX to RAX. That adds z to w and then stores it back in RAX, our return value, so then we can just return. We've done our fall through. Now if we just call case 3, remember that's where we initialize w because that's the only place we have to. So if I just have case 3 that I do and not case 2, then I'd go to L9. I would move 1 into EAX, and remember that doing a 32-bit operation automatically puts zeros in the upper bits of the register, so that just initializes RAX to 1. Then I move on down and I add RCX to RAX, right? I do my case 3 code and return from that. So this is how we can handle that fall through in a switch when we translate it over to assembly. And finally, cases 5, 6, and the default case are pretty straightforward. These are pretty much one-to-one things, right? And we just want to keep in mind that case 5 and case 6 both map to L7. We don't need to store that same code in 2 different places. So if we call case 5, we'll go to L7. If we call case 6, we go to L7. We execute the same code. For L8, that's our default. So we just set to the return value to be 2. And we return. So the takeaway on this is, again, assembly, some of it is going to be very one-to-one. Some of it is going to take some investigation. Sometimes you got to be a little bit of a detective when you take a look. If you've got a case statement and you've got some assembly, you might have to do a little bit of detective work and sort of figure out what maps to what. But if you look at these kind of different ways to handle these various possibilities, it's not too hard to map that stuff out and figure out what's doing what. So as you walk away from this video in Module 2, we want to make sure we understand control structures in C, if then else, do while, etc., the normal stuff that I'm assuming you've all seen before. We want to make sure that we understand how those things map to assembler control. The conditional jumps, the conditional moves, indirect jumps are important, and how the compiler generates code sequences to implement more complex control. And keep in mind that we've got some standard techniques of how we can map from one thing to the other, how we can get from this high-level stuff in C down to the assembly, which is a lot more low level and closer to what the processor actually does. So keep in mind, we can convert our loops. We can convert loops to do while or jump to middle forms. That large switch statements are going to end up using jump tables. We want to be very familiar with how those act. Keep in mind that sparse switch statements might use decision trees. So if, else, right? So depending on how big and complex your switch statement is, you might do something as simple as a bunch of conditions, or you might, when it gets bigger and starts getting more complex, we start moving into where we use jump tables like we saw in that example.